Our topic, the first topic for today is the alternative optima. It is also called the alternate optimal solutions. And as the name suggests, alternate optimal solutions, it means that a simplex model has like more than one solutions, and all of them satisfy alternative optima. Special cases, yes. This is lecture. This one, this one. This is a it's lecture. Okay. Yeah. So the alternative optimal solutions, in this case, the simplex model that we solve, it has so many, an infinite amount of more than one alternate solutions. And all of the solutions are acceptable. You can pick any of the solution and still the amount of profit that you get or the reduced cost that you get, it will remain same for all the solutions. So there is some, logic, or you can say a reason behind this special case. The reason is that when uh, a constraint, when a constraint falls on the same line of the objective function line, here we get the case of the alternate optima, and that line of the constraint actually exhibits all of the infinite number of points which we can use as alternate options for this solution. I will explain it using the table and as well as with the graphical. So you can go to page number 119 or 120, and we have a case of the infinite number of solutions. So the first, this is 3.52. Okay, the question is that we have a maximization function, and the function is 2x1 plus 4x2. This is the objective function, and it is subject to the first constraint is x1 plus 2x2 less than or equal to 5, and the second constraint is x1 plus x2 less than or equal to 4, and x1 x2 greater than or equal to 0. Okay, so now this is the case that we will study over here, and I will make the the simplex iterations of it, and I will show you how the solutions is not changing, yet the constraints, they change their value. The decision variable, they change their value, but the optimal solution, it will remain the same. So we can change this into a standardized form. I will just change the objective function. Okay, I will not change the constraints. I will We see that there are only slack variables that we need to put over here, and this is the standard form of the objective function that we need to put in the table. So the first table will be the basic variable, and here we get the z s1 and s2. And here we get x1, x2, s1 and s2, and here we get the right hand side of it. So in the objective function we have here is minus 2 for x1, minus 4, 0 and 0, and the right hand side is also 0. For s1 we have x1 is equal to 1, the coefficient of x2 is 2, right hand side is 5, s1 here will be 1 and s2 will be 0. The third s2 will be 1 and s1 will be 0, and x1 is 1 and x2 is also 1, while the right hand side is 4. So now we will solve this W and we will see how we can achieve so many solutions uh, in this simplex model, while the decision variables that they will change, but the optimal solution will remain the same. So the first thing is that it is a maximization function. So x2 here is the entering variable, and the leaving variable is 4 by 5 by 2, which is 2.5, and 4 by 1 is equal to 4. So this is the minimum positive. So S1 will leave the, yes, yes. No, no, we did not change the sign of it. We just made an equation out of it, which is, mandatory and you have to make it. I just converted it to, yes, yes, yes. I just, I put this side into this one and put it equal to 0. Should I do for the constraints also? Do you understand how I got the S1 and S2 also here? Like, for this constraint, I have to change it to this shape like x1 plus 2x2. It is less than or equal to, so we will add the slack variable and we will equate to 5. For the second one, we will get it like x2 plus s1 will be 0, and we can set 0 s1 plus s2, and it will be equal to 4. Now we have s1 over here, which have coefficient of 1, and s2 over here, which is coefficient of 1 over here. Now, if we go to the objective function, we see that it is equal to z is equal to 2x1 plus 4x2. Now, we can say that z minus 2x1 minus 4x2 equal to 0. Okay. Now, here we see that s1 is also 0 and s2 is also 0. It doesn't have either s1 or s2. Both of them are 0. So we put the coefficient of s1 and s2 over here as zeros. Now you got it. This is the basic simplex. Because you may be given in an exam, you may be given like just a mathematical model, and you will be asked like just make standard form of it, like putting the slack variables and equating it to 0 and these kind of things. Or you may be given like make standard form of it and make the standard table of it, just like I made it over here. So it is important thing. You need to understand. Anyway, if you have any problem with that, uh, while you are doing it again, practicing it, you can ask me and I will help it out. Okay. So now, as it is the maximization function, so here minus 4 is actually this is the entering variable. The x2 is entering variable. Now for the leaving variable, we find the ratios over here. So the first ratio is 5 by 2. We divide the right hand side by the pivot element of the pivot column. We say this is the pivot column. Okay. So here 2.5, this is the minimum one. So S1 will leave the system. And 2 here, this is the pivot key element. 2 is the key element. I must write over here that we got the pivot key element is equal to 2. Now, as this is the pivot row, we must update it. So the new pivot row or S1 star new pivot row, we actually this X2 will move over here in place of X1. So I must do the calculation first and then update this table on the next page. Okay, I will first do the calculations. I will not make the table first, just like I did in the question that you asked, you were confused about. So I will make the calculation first and then I will update the table. Okay, so the pivot row is equal to the old one divided by 2. So the old one is 1, 2, 1, 0, and 5. We divided it by 2. So we get here is 1 over 2, 1 over 2, 0, and 2.5. This is the new pivot row. Now we have got new pivot row. We must update the Z and S2 according to the new pivot row. So I will update both of these. Now the new Z or Z row is equal to old Z row minus pivot column coefficient into new pivot row. So now the old Z is minus 2, minus 4, 0, 0, and 0 minus the pivot coefficient is minus 4 and the new pivot row is 1 over 2, 1, 1 over 2, 0, and 2.5. So what we get over here is we get minus 2 plus 4 divided by 2 is 2. So minus 2 plus 2 is equal to 0. Minus 4 plus 4, it is also 0. 0 minus 0 plus 2 is 2 and 0 plus 0 is 0 and 0 plus 4 into 2.5, it is equal to 10. So this is the new Z row. Now we also need to update the S2 row. So new S2 row is equal to, we will use the same formula, old S2 minus pivot column coefficient into new pivot row. So the old S2 is equal to 11014. 1101 and 4 minus the pivot column coefficient here is 1 and the pivot row is 1 over 2, 1, 1 over 2, 0, and 2.5. So what we get over here is one minus one over two is one over one minus one is zero. Is now we will update table R W. So here we get Z. Here we will put x2, and here we will put s2, and x1, x2, s1, s2, right hand side our solution and ratio. Now the Z table, Z is here is 0, 0, 2, 0, 10. 0, 0, 2, 0, and 10. X2, the X2 row or the pivot row is 1 over 2, 1, 1 over 2, 0, and 2.5. The S2 row new is 1 over 2, 0, minus 1 over 2, 0, and 1.5. Okay. Now the optimality actually has reached, but still, we will do another iteration of it, and we will see that the answer of it, that the solution here, which is 10, it will not change. Whether, we will do so many iterations of it, but the solution will remain same. However, the values of here, like this solution is for, we get x1 is equal to 0 here, x2 is equal to 2.5, and z is equal to 10. And we know that the objective function over here is maximize z is equal to 4x1 plus 2x2, what 2x1 plus 4x2. So 2 into x1 is 0 plus 4 into x2, which is 2.5, and we get is 10. Now we will do another iteration of it, getting x1 as entering variable, and we will see that the answer for the overall answer, the right hand side, it will not, and x2 will change its value. For example, now here x1 is the least one, so x1, because x2 is already over here, we can only take x1 as entering variable. So taking x1 as entering variable, we see that it is 2.5 divided by 1 over 2, which will give us 5, and it will be 1.5 divided by 1 over 2, and it will give us 3, I guess. So this is the minimum one, minimum positive. Okay. So S2 will leave the system. X1 is entering and S2 is leaving. So this is the pivot row, and this is the pivot column, and this is the pivot element or key element, 1 over 2. Yes. We do not have x1 over here. Now we will, because x1 is entering variable, so x1 will move to this point, and x2 will leave the system. Yes, first we had x2 as entering variable, so x2 entered here and s1 left the system. But now x1 is entering and s2 is leaving, So I will update it over here. And we will have like z x2 and then x1. Here we will be, because here in the last one, we see that we have like one negative value. So whenever in the last column, in the last row, or in any column of this table, you have a negative value. Yes, if we have negative value, it means that the the optimal solution has not yet arrived. Like it can have like another optimal solution. This is a condition. Yes, when there is a negative value over here, you can say that the optimal solution has not yet arrived, or it has an alternate optimal solution. Okay. So now we will have here is z x2, and now x1 will enter here, and here it will remain the same, like just x2 s1 s2. We will have like solution over here on right hand side, and we will have a ratio over here, but we don't need to have ratio in this because this is the last iteration. It can be last, it cannot be last, you can have another iteration too, because I think that we will get another some negative value either over here or either over here, but we will get some negative value, I hope. So now, yes, because we don't have any x1 over here in this column along with z, so it means that x1 is 0. We have x2 over here, and against the x2 on the right hand side we have 2.5, so it means that 2.5 is the value for this variable x2. That is how you interpret this table. You interpret the values of the variables and z. Here is z, and against the z we have right hand side is equal to 10. It means that the optimal solution or the optimal value is 10. Okay, so now this one is the uh, pivot row. So we will first find the new pivot row. New pivot row is equal to old pivot, or you can say that and key element. We can say that now we know that the old pivot is the S2 row. S2 row divided by key element. Now the S2 row over here is 1 over 2 0, 1 over 2 0 minus 1 over 2 1 and 1.5, and it will be divided by 1 by 2. So we will get here is 1 0 minus 1 2 and 3, I guess. Okay, so now we will use this new pivot row and update it over here. Now this is x1 is the pivot row over here. So the pivot row now becomes 1 0 minus 1 2 3. 1 0 minus 1 2 and 3. Now again we see that for s1 the value is minus 1. It means that we can still make the iterations. But I just want to express the case here that it has an alternate solution. It has infinite number of alternate solutions. We will just solve it for two solutions, but you can solve it for like tens and hundreds of solutions, and it will not end. That is the case of alternate optimal solution, or you can say that alternate optima. This is the scenario. So now we will update the z table and x2 table. Now new z is equal to old z minus pivot column coefficient into new pivot row. Okay, so the new pivot row is here. Coefficient and old z we need to put. So the old z we got was 0, 0, 2, 0, 10. 0, 0, 2, 0, and 10 minus the pivot column coefficient is 0. So 0 into the new pivot 1, 0 minus 1, 2, 3. It will become 0. So what we get over here is the same 0. This new z will be equal to the old z row. It will repeat. You got it? You see that this z row and this z row both are actually same. But let me do one more step, and we will come to the conclusion. Then we will discuss it a little bit in graphical manner. So in graphical method, you will understand it more better. That how these solutions are coming. Okay, we just need to update it for x2, and then will we come to the conclusion of it. Now, the new x2 row is equal to old x2 minus Lareka. Sorry, my kid was here, so he was disturbing me. So I have to. Okay. So old x2 minus pivot column coefficient into new pivot row. So the old x2, we have the pivot column coefficient, new pivot row, and old x2. The old x2 is 1 over 2, 1, 1 over 2, 1, 1 over 2, 0, and 2.5. And the pivot column coefficient here is 1 over 2. And the new pivot row is 1, 0, minus 1, 2, and 3. So what we get over here is 1 minus 2, 1 divided by 2 minus 1 over 2, which will become 0. 1 minus 1 over 2 into 0 is 0. So 1 minus 0 is 1. 1 over 2 minus 1 over 2 into minus 1 is 1 over 2 plus 1 over 2. So it will become 1. 0 minus 1 over 2 into 2. So it becomes 0 minus 1, and it will be equal to minus 1. 2.5 minus 1 over 2 into 3. So 2.5 minus 1.5 is actually 1. So now we will update the table and put the x2 new, which is 0, 1, 1 minus 1, 1. 0, 1, 1 minus 1, and 1. So now we are getting the right hand side is equal to 10. It is not changing, but x2 is 1 and x1 is 3. So we have two solutions over here. Okay, this is the x1, this is x2, and this is the z value. First solution is we had x1 is equal to 0 and x2 is equal to 2.5 and z was 10. The second solution is that we have x2 is equal to 1 and x1 is equal to 3 and the solution is 10. So now you can, you can make a number of iterations, an infinite number of iterations, and the x1 and x2 value will be changing, but the z value, it will remain 10. So this case is called alternative optima or alternate optima. Do you understand it now? Like in this one, we have maximized z is equal to 2x1 plus 4x2. So putting the value like 3, 1 over here, 2 into 3 plus 4 into 1, so it will give us 10. Similarly, putting these values, we get 2 into 0 plus 4 into 2.5. It also gives us 10. So the optimal solution is 10, but the values of the decision variables, it will keep changing. Yes, 2 into 3 is 6 and 4 into 1 is 4. So 6 plus 4 is 10. And here we put 0 and 2.5. So 2 into 0 is 0 and 4 into 2.5 is 10. So we are getting the same solution, but we are getting the alternate values for the x1 and x2. So x1 and x2 will be changing, keep changing, like you can have like 1,000 of solutions. But the ultimate solution, that is the z, will remain the same. So this is the alternate optima. Now I can also, I want to do it using the graphical method. So you understand it, like if in paper on a graph and the teacher asks you that prove that this is the kind of alternate optima case in this question. So you can just have a look at it and you can point it out. It's okay, like this constraint is along the objective function, and that is why it is the alternate optima situation over here. So in graphical, it will just take like 2 minutes for a graphical method. We have x1 plus 2x2 equal to 5 and x1 plus x2 equal to 4. So taking the first constraints, first one we will get is x1 plus 2x2 is equal to 5. Putting x1 is equal to 0, we get x2 is equal to 2.5, and x2 is equal to 0, we get x1 is equal to 5. Similarly, in second constraint, we have is x1 plus x2 is equal to 4. So for x1 is equal to 0, x2 is equal to 4, and alternatively, for x2 is equal to 0, x1 is equal to 4. Now, in the graphical method, we will plot this using a graph. So this is our x1 and the y is our x2. Now we will plot these points 0 and 2.5. So for x1 is equal to 0, let us suppose that it is 1, 2, 3, 4, 5, 6, and so on. We graduated. And similarly, we graduated over here 1, 2, 3, 4, 5, and 6. And this is our 0, 0. So now for the first, x1 is equal to 0, x2 is equal to 2.5. So this is the point over here between 2 and 3. And for x2 is equal to 0, x1 is equal to 5. So this is the point. We will, join these points. Now this is the C1 constraint, constraint number 1. And the line is x1 plus 2x2 less than or equal to 5. This is the line. Now for the x2, the constraint 2, we have for x1 is equal to 0, x2 is equal to 4. And for x2 is equal to 0, x1 is equal to 4. So now we will join these two. Now the solution is along this line, this and this. This is the solution. All the solution lies over here. And the objective, the solution actually, the optimal one, lies where both the constraints actually, they cross each other. And on this line, this is the solution line. And this is also the constraint 2 line. Both of them lie on the same plane. So the alternate solutions lying on this point, any point you select on this line, it will give you a value of 10. The x1 and x2, they will keep changing, but the optimal solution will be 10. So this is the line of coincidence. That is how it is interpreted in using the graphical method. Now you understand it? Do you hear me? I just, just like we do the graphical method, in the first constraint, I put x1 is equal to 0 and I found x2 for that x1 is equal to 0. And similarly for x2 is equal to, I found the value of x1. In the second constraint, I found the value of x2 when I put x1 is equal to 0. And similarly for, if you put x2 is equal to 0, I found the value of the x1. And then we plotted both the lines. And here we see that the optimal solution line, this is the optimal solution line, this one. This is the optimal solution line. And this portion of the constraint 2, this portion of constraint 2 lies just above the objective function line. Yes. So these getting any point on this line, any point on this line will give you an answer of 10. So this line actually have an infinite number of solutions. The end solution will be same, but you can have infinite number of x1 and x2 combinations. Just like we had over here, we had just like two combinations. X1 is equal to 0 and x2 is equal to 2.5 and x1 is equal to 3 and x2 is equal to 1. You can have like a number of solutions. For example, the third solution that I can have is like, for example, if I put x1 is equal to like, for example, if I put x1 is equal to 2, then what will be the value of x2? So x2 is equal to 10 minus x1 divided by 4. So x1 is equal to 2, so 10 minus 2 is equal to 8, 8 divided by 4, 2. So 2, 2 is also a solution. It will give us the value of 10. Sorry, it will not give you the value of 10. If x1 is equal to 2, we have an objective function of for 2x1 plus 4x2 is equal to 10. Because objective value is 10, so I will put over here 2 into 2 plus 4x2 is equal to 10. Okay, so it will give us 10 minus 4 divided by 10 minus 4 is 6. 6 divided by 4 is 3 by 2. So if we put x1 is equal to 2, the x2 value is 3 by 2. It will give us a solution of 10. You can have like a number of solutions for it. Yes. So this is the alternate optima or alternative optima. Now the third case is the unbounded solutions. So for unbounded solutions, which does not have a limit or a boundary. Like one constraint of it, any constraint of an optimal solution, it can have a number of values. Increase the value of that variable, yet you will get, so many solutions for it unboundedly. It will not have a boundary. For example, we have two variables, x1 and x2. And if, we change the value of one variable, the objective function value is also increasing or decreasing, depending on how much you are increasing or decreasing the value of the variable. But in unbounded solutions, the one variable, it can be increased like infinitely. Yeah, we know that in the simplex method or in linear programming, we have constraints. So for example, if we increase the value of some variable, at some point it will cross the constraint. It will not obey the constraint. For example, we have a constraint over here like 2x1 is less than or equal to 10. Okay, so now the value of the x1, it cannot be greater than 5. If we put like 6 value, if you put x1 is equal to 6, if we put x1 is equal to 6, it will get us value of 12, which is greater than 10. So it will not obey the constraint if x1 value is greater than 5. So this is not unbounded, this is bounded. But in unbounded solutions, we have some constraints that if we change the value of their decision variable, it will not contradict any constraint. It will obey the constraint. It will satisfy those constraints in any condition. Let me show you using a regular example from the book. Then you will understand. Do you understand like what I just said regarding the unbounded solutions? Bigger than 10, yes. But in unbounded, this thing does not happen. This is the bounded one. This is the bounded case. This is bounded, but in unbounded, yes, you can put any value, you can put any number, and it will not, contradict the constraint. It will satisfy it at any condition. No, there is constraint. There is constraint, but the condition is that it will satisfy whether whatever value do you put for a single variable, not two variables, only one variable of the constraint. Like we have x1 and x2, we will have a condition of it. For example, we have a constraint x1 minus x2. X, yes, I will. This is the example like 3-5.3, and it is page number. Let me show you the page. It is page number 121. It is page number 121. They make the iterations also. Yeah, it will have like two iterations, not more than two. Yes, it will have two iterations, maybe. Yeah. Yes, and it will not have more than two iterations, but it will also have like graphical method. But in graphical, you will understand it like more. Should I do the graphical or the iterative one? Okay, I will let me do the graphical one first, so you can understand like the behavior of that variable using graphics. But then I will come to the table method, and you can have an experience of it too. So the unbounded solution actually means that a variable can be increased indefinitely without contradicting the constraint. It will not break any constraint. It will not break the rules. Yet you can improve it. You can, maximize it up to infinite value. And the reason, yes, okay. And the reason for this unbounded solution is that the model is either it is poorly constructed, some key constraints are missing from the system, like you didn't study the system completely and just put one or two constraints in it, and you get unbounded solution. You are not bounded by, you do not get any region for the feasible solution. It is an open area. And the third one is that like the constraints coefficients, they are not well chosen, they are not accurate. Like we say that the cost for making a mobile is like $200, so I can assume it like 121 unbounded solutions. So I will solve it using the graphical method first, so you can understand like how this is the unbounded solution. So as it is two variables, we must need to graph it. This is our x1, this is our x2. Now, taking the first constraint, we get is x1 minus x2 is less than or equal to 10. So put x1 is equal to 0, we get x2 is equal to minus 10. Okay. Now, putting x2 is equal to 0, we get x1 is equal to 10. The first one, x1 is equal to 0, x2 is equal to minus 10. For example, this is 5, this is 10, this is 15. So here, this is minus 5, this is minus 10. Okay. So this is 0 minus 10, this is the line. And for x2 is equal to 0, x1 is equal to 10, and like this is 5. So this is constraint actually. This is a constraint. Now for the second constraint, we have 2x1 equal to 40. So x1 is equal to 40 by 2 is equal to 20. So x2 is equal to 0 here and x1 is equal to 40. So this is, for example, 20, this is 30, and this is 40. So this is the point. Okay. And for x, this is the constraint circuit. Now, this area is infeasible region. This area is also infeasible. This is also infeasible. But this one area, this is the feasible region. Now we see that this area doesn't have any boundary. The value of x2 can be, any point in this area. You see it? Yes. But this is the infeasible. Yes. So this is the infeasible area. Which one? Uh, this one. This one. Actually, it will be not on the 40. It will be on the 20 over here. It will be here actually. Again. So this is a non-feasible area. This is only the feasible region, and you see it doesn't have any kind of boundary. So you can increase the value of x2 indefinitely, and the objective function will also increase. So these kind of solutions are unbounded solutions. You see it? Now it has some conditions in the W form. So you must know those conditions. So when those conditions arrive, you can make a verdict that this equation or this simplex problem has unbounded solution. You can just right away say that it has unbounded solution. So it has some kind of conditions or two. Hello? Yes. Why this is unbounded solution? It is because x1 is bounded. X1 cannot be greater than 20 over here. But x2 is not bounded. X2 can attain a value of infinity. X2 can go up to infinity. You see, x1 here is limited up to 20. But if you see the value of x, this one, this is not feasible region because this is infeasible region because it does not satisfy this constraint that we draw the first constraint. Only this area satisfy both the constraints. This one and this is the area. I must, I will pinpoint it to you. This one, this one, this one, and this one. This is the area. This is the feasible region. This is not feasible beyond this line. Beyond this line towards this is not feasible. This is not feasible because it is contradicting this one. This is also infeasible. This is also infeasible because it is contradicting this one constraint. Yes. So that is how this unboundness works. But I will, now make this, in tableau form, and I will show you the conditions of it. So you know that when these conditions arrive, you just, you know that now this thing has happened. So now this is an unbounded solution. It cannot have like a bounded solution. You can say you may be given a final tableau, and you will be asked by your teacher that tell me that how this is an unbounded solution, or tell me that whether it is bounded or unbounded. So you can just looking at it, you can say that because this happens in the final tableau, so this is the unbounded solution. This is the same procedure as simplex. It is not some kind of okay. So as I was talking about this thing that I just did it in my mind and I didn't write it over here, but now I wrote it over here. Actually, I made the equation in my mind and I put the values over here, but for your convenience, I just put it down and made an arrow that which row represents which one constraint an objective function. Okay, so for the first iteration, as it is maximization function, so x1 over here, this is the maximum negative. So this is our entering variable, and for the leaving variable, we will have like 10 by 1 and 40 by 2. So this is the 10 is the minimum ratio. So S1 will be leaving the system and will be replaced by X1. But first we need to calculate and then we will update this table. So for the calculations, we have the new pivot row which is equal to the old one divided by the key element or pivot element. Now this is the pivot column. This is the pivot row. So 1 is the key element and the old pivot row is equal to 1 minus 1, 1, 0 and 10, and it will be divided by 1, which will remain the same. It will not change. Now we need to find two other rows. First one is the updated 0, Z row, new Z row and new S2 row. Now the Z row will be equal to the old one minus pivot column coefficient into new pivot row. Now the old one is minus 2, minus 1, 0, 0 and 0 minus the pivot element is minus 2 into the new one is minus 1, 1, 0 and 10. So here we get minus 2 plus 2 is 0, minus 1 and minus 2 is minus 3. 0 into 2. 0 plus 2 is 2. 0 plus 0 is 1. 0 plus 2 into 10 is equal to 20. So this is the new Z row. Now new S2 row is equal to old row of S2 minus pivot column coefficient into new pivot row. So the old S2 row is 2001 and 40 minus the pivot coefficient is 2 over here, and the new is 1 minus 1, 1, 0, and 10. It will be equal to 2 minus 2 is 0, 0 plus 2 is 2, 0 minus 2 is minus 2, 1, 0, 1 minus 2 into 0 is 1 actually, 4 into minus 2 into 4 minus 20, 40 minus 20 is 20. So this is the new S2 row. Now we will make the table and update it. So the table update is here we say the basic variable. This is the Z row. Now x1 will be moved here, and we have S2 row over here. X1, x2, S1, S2. We have the right hand side, and then we have ratio. Now the Z row, new Z row is equal to 0 minus 3, 2, 0, 20. 0 minus 3, 2, 0, and 20. So the answer is updated from 0 to 20. Now x1 is the new x1 row, or the new pivot row is 1 minus 1, 1, 0, and 10. And the new S2 row is 0, 2, minus 2, 1, and 20. Now we have a negative over here. So the next entering variable will be x2, and the leaving variable will be and divided by minus 1. It gives negative. So negative is actually ignored, and 20 by 2 is equal to 10, which is positive. Minimum positive is this one, so S2 will leave the system. Now this is the last iteration, then we will conclude it, and inshallah we will go towards the infeasible. Old divided key element. Now the key element, yes. Okay, so now the new pivot is equal to all divided by key element, and the old pivot row, yes. Okay, so the old is equal to 0, 2, minus 2, 1, and 20, and the key element over here is 2. So we get is 0, 1, minus 1, 1 over 2, and 10. So this is the new pivot row. Now new z is equal to old 1 minus pivot column coefficient into new pivot row. Now the old z is equal to minus 2 minus 1 and triple uh, sorry 0 minus 3 minus 3 2 0 and 20 minus the pivot column coefficient is minus 3, so minus 3 into, and the new pivot row is equal to 0 1 minus 1 1 over 2 and 10. Using this row operation we will get is 3 minus 3 plus 3 is 0. 2 minus 3 is equal to minus 1. 0 plus 3 by 2 is equal to 1.5. 3 by 2 or 1.5, one and the same thing. And then 20 minus and minus 3 into 10, it will become plus 3 into 10, 30, 20 plus 30 is equal to 50. So the new z is improved and the answer right hand side is now 50. Now we need to have the new x1 row because x2 is already the pivot, so we just need to update the x1. So new x1 is old x1 minus pivot column coefficient into new pivot. Now the old x1 in the previous one is 1 minus 1 1 0 and 10, and the pivot column coefficient here is minus 1 because it is below the x2 column, and the new pivot is 0 1 minus 1 1 over 2 and 10. Doing this row operation, what we will get is 1 plus 1 into 0 is equal to 1, minus 1 plus 1 into 1 is equal to 0, 1 plus 1 into minus 1 is equal to 1 plus 1 into 0, 0 into plus 1 into 1 over 2 equal to 1 over 2, and 10 plus 10. Now this is the updated x1 row, new x1 row. Now I'm making the W. The W will be variable, basic variable, z, x1 is already there. Here we will put x2, here x1, x2, s1, s2. And we will have here is right hand side and here the ratio. Okay, so now the z, new z is 3, 0, minus 1, 1.5 or 3 by 2 and 50. x1 new is 1, 0, 0, 1 over 2 and 20. And x2, the new pivot was 0, 1, minus 1, 1 over 2 and 10. Now this is the final solution of it. but it is not final. Why it is not final? Because here in the S1 column, we have a negative over here as well as a negative in the last row. So whenever there is a negative number in the last row or any column of it, it means that the solution is unbounded. And which variable which will actually gets an infinite amount of values, it will be the variable against which there is a negative number in its row. Here if we see the x2 row, which one? This one? This? This is 3. This 3. Okay. So against the z, we see that it has a -1 over here. So it means that the solution is unbounded. Similarly, and against the basic variable x2, we have a negative number in its row. It means that the x2 variable is actually indefinite. It can have an infinite number of values, and yet it will satisfy the second constraint. Sorry, the first constraint. So these are the two conditions. Yes, both of them are unbounded because it has -1 and -1. Yes, z is also unbounded because when we change the value of x2, it will also improve or deprove. For example, we this is a maximization problem, so making the value of x2 like increase, it will also increase the value of z. So both of them are unbounded, the z as well as the x2 variable, while x1 is bounded. You see all the values are positive over here. So these are the basic signs, basic conditions which we see over here. And if we see if there is any negative value in the slack variables or in the slack columns, so against that variable, it is the unbounded. So x2 here is unbounded as well as the z is unbounded. So this is not the final solution of it. It is unbounded. It can have like an infinite number of solutions, and the value of the x2 can vary by. And how it can vary, I will show you. I will show you it. For example, here in this question, we have this constraint x1 minus x2 is less than or equal to 10. x1 minus x2, it is less than or equal to 10. Now, x2, x1 over here is 20. 20 minus x2 is less than or equal to 10. Now put the value of x2, whatever you want to, it will satisfy the constraint. For example, uh, uh, let let's the value of x2 be 1000 or 100. So 20 minus 100, it is equal to minus 80, and it is still less than or equal to 10. So it is satisfying it. You can make its value like 1000, 1 lakh, 10 lakh, and crore up to up to infinite. It will still it will be less than or equal to 10. No. X1 is bounded. X1 is 20. You cannot change it. Only X2 is unbounded. Yes, the problem is that only X2, because here we have a negative number. So only X2 is unbounded. X1 is not unbounded. X1 is bounded. X1 cannot have, X1 has a value of 20. Yes, yes. So this is how the unboundedness work. Now I will move to the infeasible solutions, and eventually after that I will move to the sensitivity analysis. Okay. Now the fourth case is infeasible solution. This is kind of relatively easy. The infeasible solution is actually kind of easy if we see the other things. So in that case, infeasible looks a bit easy. So this is actually the fourth case of the special cases. So it is infeasible when the constraints are actually inconsistent. Inconsistent means that some of the constraints have like greater than or equal to, and some of them are less than or equal to, or all of them are greater than or equal to. Then the constraints are said to be inconsistent. If all of them are, if all are less than or equal to, it will always give feasible solution, because you have set the boundaries of it. Like it should be something like you have a right hand side of it, and you say that it must be below than this, and you know that x1 and x2 must be greater than or equal to. For example, we have a constraint that like for example x1 must be less than or equal to 100, but we also have a constraint that x1 must be greater than or equal to 0. It means that the x1 will lie somewhere between 0 and 100. So it will always produce a feasible solution if the situation is in less than or equal to condition. But if there is a mix of it and more of the constraint are greater than or equal to 0, then the solution will be infeasible. There will be infeasible solution. It is not necessary that it will produce infeasible solution, but depends upon the cases. Okay, and the most important condition of it is if one of artificial variable is positive or greater than 0 in final iteration. This is the most important case. If we reach to the final iteration of a tableau of a simplex method, and then one of the artificial variable, like I told you that it must be like it must have like one greater than or equal to sign. If there is a greater than or equal to sign, then we introduce an artificial variable to it. So if that artificial variable is greater than 0 in the final iteration, then it is infeasible solution. You understand it? Yes, when the artificial variable, we know that we have like we have a table in which we have basic variables over here. Okay, we have z over here, we have s1 over here, we have x1 x2 over here. Okay, if the artificial variable is over here, for example, the first one artificial variable is also over here, and here in the right hand side it has a value of like 1, 2, 3, and so on, and it's not 0, then this case is called the infeasible solution. You understand it? No, this cannot be shown on the graph. The reason is, yes, it cannot be shown on the graph, but it is just for the table method. Because RA, yes, because we do not add the artificial variables in the graph, in the graphical method. We only put it in the simplex and the big M method or the two-phase method. In the graphical, we do not put any kind of, slack variables or surplus variables or artificial variables. We only put it when we do the question by simplex method or our advanced simplex method like big M or two phase method. Do you understand it now? Yeah, just you need to understand that if a W is given and we have an R over here or A over here, whatever the teacher may represent it against, and we have on the right hand side it has some positive value, it means that it is infeasible solution. That is the main condition for it. Okay now. Yes, and now we will move to the the sensitivity analysis, and I will do just the first part of it, and the other three parts of it I will do inshallah tomorrow. So should I start sensitivity? Okay. Okay, the sensitivity is used by two kind of procedures. The first one is the graphical one, and the other one is the tableau one or the algebraic one. Today I will just do the graphical one, and sensitivity is when you see that how the objective function value, the z value reacts to any change in the objective function coefficients or the right hand side of the constants. For example, we have a function like maximize z is equal to 4x1 plus 6x2. Okay, or I should write the example of the book so you can see it over there also. For example, here we have is 30x1 plus 20x2. Okay, and the constraints are 2x1 plus x2 is less than or equal to 8, and x1 plus 3x2 is also less than or equal to 8. And this is the machine one time, and this is the machine two availability. Okay, so this is the shift hours of this machine. It means that the first product consumes 2 hours of the machine, and the second product consumes only 1 hour of the machine. And the total hours of the machine one, are 8 hours. It means that it is only available for 8 hours shift. The second one is that the product two actually consumes 1 hour on machine two and 3 hours on machine two. And the total time that machine two is available per day is 8 hours. Now the sensitivity analysis actually is, first is it is graphical and algebraic. Graphical is when we have two variables, and algebraic is when we have three or more than three variables. However, it can also be used for two variables. Okay. Now, sensitivity is based on two things. The first thing is that we change the right hand side RHS of constant. And the second one is we change coefficients of objective function. It means we either, for example, we say that now the machine one is available for like 10 hours or 9 hours. And then we see that how much profit it can improve by utilizing machine one, not 8 hours, but 10 hours. And the second one is, for example, the product one, you know, it makes a profit of $40 and not $30. And then we see how much the profit is improving. So the first case we will do is when we change the right hand side of the constraints, and we will do it algebraically, graphically. Okay, so now this is the original equation. Okay, I will split it into half, and I will say over here is original, and I will say over here is change in constraint 1 right hand side by 1 hour. I change this 8 to 9, and let the all the other things remain the same. So the original will be maximize z is equal to 30x1 plus 20x2. Okay. Now the constraint is 2x1 plus x2 is equal to 8. In algebraic, we do not add any slack or surplus or artificial variable. Okay. So let x1 is equal to 0, then x2 is equal to 8. Now if x2 is equal to 0, then x1 is equal to 4. Similarly, in constraint 2, we have x1 plus 3x2 is equal to 8. Now if x1 is equal to 0, then x2 is equal to 8 by 3. Now, if x2 is equal to 0, then x1 is equal to 8. This is how. Now we will graph both of these situations, the original one and the change in constraint, into a single graph, and we will see that how much the objective function, the maximum profit that we achieve, that is changing with this change in the. Now we will take the change in the constraints. The change in constraints can be taken as maximize z is equal to 30x1 plus 20x2, and it is subject to 2x1 plus x2 is less than or equal to 9. I just increased 1 hour in one time. Now, and the second one, it will remain the same. Okay. Now, using graphical method, we see that 2x1 plus x2 is equal to 9. If x1 is equal to 0, x2 is equal to 9. Now, if x2 is equal to 0, x1 is equal to 9 by 2. For the other one, we see that x1 plus 3x2 is equal to 8. Now, if x1 is equal to 0, x2 is equal to 8 by 3. Just like we found it over here. Now, if x2 is equal to 0, x1 is equal to 8. We will plot this one situation and this one situation on the same graph, and we will see how much the objective value of this function increases with a single unit increase in the number of hours of machine 1. Now, we will make, yes, the second constraint will remain like it will. What? So x1 is actually 9 by 2, na? It is equal to x1. If x2 is equal to 0, if we put x2 is equal to 0 over here, we get 2x1 is equal to 9. So x1 is equal to 9 by 2. So this is the value of x1, 9 by 2. Now we will plot this situation and this situation on the same graph, and we will see that how much the objective function value is changing on both the conditions. Now we have a graph over here, and this is our x1 and this is our x2. Now first we will plot the original condition. The original condition is that for x1 is equal to 0, x2 is equal to 8. Now we will see that this is for example 2, this is 4, this is 6, this is 8, and this is 10. Okay, similarly here it is 2, 4, 6, 8, and 10. Now we see that x1 is equal to 0 and x2 is equal to 8. So x1 over here it will be 0 and x2 will be equal to 8. So this is the point that it gives us. Now for x2 is equal to 0, x1 is equal to 4. So for x2 is equal to 0, x1 is equal to 4. So we will join these 2 points. So this is the constraint 1 of original. Okay. Now we will see that what the second constant plot is. For the second constant, if x1 is equal to 0, x2 is equal to 8 by 3. If x1 is equal to 0, x2 is equal to 8 by 3. For by 8 by 3, it gives us a value of 2.666 cost. That is the coefficient of the objective function. These two are the things that we discuss in the sensitivity analysis. So here in this, we made a change. We are just analyzing the case where we change the right hand side of the constraint. So here we change one constraint from 8 to 9, and then we plot the original and the new one with changes on the same graph and see how much the z value is increased or decreased. So here in the graph, the very first value that we plotted actually was this one. The first constraint says that for x1 is equal to 0, x2 is equal to 8, and for x2 is equal to 0, x1 is equal to 4. So we meet the point 8 with the 4. Okay. Now the second constraint is that for x1 is equal to 0, x2 is equal to 8 by 3, and for x2 is equal to 0, x1 is equal to 8. So first of all, the second one is simple. So for x2 is equal to 0, x1 is equal to 8. So this is the point that we log here. Now the first one is for x1 is equal to 0, x2 is equal to 8 by 3. So 8 by 3 will give us 8 divided by 3. It is equal to 2.66 or 2.67. So here, this is the point. So we will, meet this point and this point together and draw a line in between. So here we draw a line over here. So now this is the original scenario. So both of them are less than or equal to. So here the direction is towards the origin, and this is the optimal point. So this is the feasible region. This is the optimal point because it is the intersection of the both the constraints. Now on the same, because we have the second constraint is similar, but we have only changes the right hand side by one in the first constraint only. So we will plot the first constraint also. Now plotting the first constraint, we see here is that in the changes constraint scenario, we have for x1 is equal to 0, x2 is equal to 9. So for x1 is equal to 0, here it will be 0, x2 is equal to 9. So it will be somewhere over here. So we mark this point. Now we see that for x2 is equal to 0, x1 is equal to 9 by 2. Now we x2 is 0 over here and 9 by 2 is 4.5. So it will be somewhere between 4.5 or 9 by 2. So this is the point that we mark. Now we will join this point to this point, and this is the line. Now for this scenario, this one is the optimal region. Let's suppose that this is the optimal O of our original, and this is the optimal N for new. Okay, we see that the Z value has been changed with the changing the right hand side of the constraint. Now how much this value is changed, we need to find the z value for this one and the z value for this one. So the z value for the first one will be, let me make it this way. So it will be somewhere x1 is equal to and x2 is equal to. The x1 over here, it will be original. It means that we haven't changed over here in the constraint, and we have a change over here in the constraint. This constraint is small, is similar for both. Only this constraint is changing. Yes, it is also changing the optimal region. The first one, in the first one, the optimal region is this one. And in the second one, the optimal region is a bit longer. It also includes this region. Sorry? No, only these two. For the original, we can plot it on different, different graphs. We can plot the first problem on the different graph and second one on the different graph. I just, chose to graph it on the single, XY plane because we wanted to see how much the optimal value is changing, how much drift is there. You see the optimal values have changed from this to this point. This is when the original scenario is used. And this is the optimal region when the second one scenario is used. Now this point is actually x1 is equal to x1 is somewhat 3.2 over here, and x2 is somewhat like just below 2. It is like 1.6 over here. So for the optimal O, we have x1 is equal to 3.2 and x2 is equal to 1.6. Now for the optimal N, we have it is somewhere between 4 and 4.5. And the x1, x2, sorry, it is somewhat 1.4 or something, okay? And this point x1 is like in the book it is like 3.8. But obviously we don't have like properly graduated over here, so we are getting a bit change over here. But it is 3.8. So there in this optimal N, we have x1 is equal to 3.8 and x2 is equal to 1.4. Now the z value here is equal to we have 30 into 3.2 plus 20 into 1.6, and it gives us a value of 128. Okay, now here the z value, z is equal to 30 into 3.8 plus 20 into 1.4, and it gives us 142. Now see that if we change the constraint from 8 to 9, it means that like by 1 unit, the Z value changes from 128 to 142. It improves from 128 to 142. So we need to calculate the rate of change. Rate of change is equal to, now the 142 minus 128 minus, we change it from 8 to 9. So the total change is $14 per hour. What it means is that if we change the resources by 1 unit, like the machine time from 8 hours to 9 hours, the unit profit that is increased is $14. It means that if we change the machine time from 8 to 10, like 2 hours, the total change in the objective function will be 14 into 2, $28. If we change it from 8 to 11, it means 3 hours. So the total change will be 14 into 3. It will be equal to $42. What it means is that if we change, it means that if we change the value from 8 to 10, like 2 hours for the machine 1, the Z will be equal to 128 plus 28. It gives us $156. If we change 8 to 10 hours change. Now this, if this change is from 8 to 11 hours, like 3 hours of change, then it is equal to 128 plus 14 into 3. So 128 plus 56, so it will give us, sorry, $42. It will give us like $170. So we can, if you need, if you know the rate of change, if you know this value, we can easily calculate how much it is going to change the objective value if we change like the time by 8 hours, by 7 hours, by 100 hours, by 5 hours, no matter how many you want to calculate. Do you understand it? No. Rate of change you can find for any of the problem. Like for example, you want to, like for example, you have a business and you operate it like 8 hours a day. Okay. For example, I have a shop and I operate it like for 8 hours in a day, only 8 hour shift. So I want to calculate if I operate it for 10 hours, what will be the profit increment? What will be the profit that I achieve? This is the sensitivity analysis. You understand? Okay. I will, inshallah, I will for tomorrow, I will first summarize it, this first case, and I will then go on forward. I will also do it again in case you want it. If you are, okay with it, I will not do it, but I want to, summarize it for tomorrow too. because we had a break in between, and if there is a break in between this, the things got a little bit, it's a bit hard in understanding then. So tomorrow, inshallah, before starting the going for the next topic, I will first summarize this thing, and then going after this, we will be joining the other topics too. And inshallah, I will be doing two more topics in the sensitivity tomorrow, or maybe three. But the algebraic one is like kind of complicated, so I want to focus on that. This graphical one is not that uh, complicated and not that important. Maybe it is not that important to teacher too, because he will focus on the dual or shadow prices and these kind of things. So that is a bit complex, and teacher will also want you to know those things. Okay. Yeah, so inshallah for tomorrow I will be doing this again, inshallah, up to some extent, and then I we will be going towards the changing the coefficients, and then we will be going to the algebraic method. Then this chapter will be almost over, yes, and then we will go for the duality and the post-optimal analysis. Yes, do you want to ask something? Okay, and also please send me the the content, the updated content of the teacher, like what. Okay, and I guess he's already started chapter number 4, the duality and the post-optimal analysis, because I saw a topic or two in that thing too. Okay, so that's all for today, inshallah. Inshallah, inshallah. And I also had a request